2.5 Exponential Functions. Objectives for section 2.5. The student will be able to graph and identify the properties of exponential functions. The student will be able to graph and identify the properties of base E exponential functions. So these are special exponential functions. The student will be able to apply base E exponential functions, including growth and decay applications. The student will be able to solve compound interest problems. So that's a kind of growth problem. Compound interest is an application of these exponential functions. Okay, so first objective, the student will be able to graph and identify the properties of exponential functions. F of x equals b to the x, b not equal to 1. And we want b to be positive. Defines an exponential function for each different constant b called the base. The domain of f is the set of all real numbers. Okay, so if you've got an exponential and the question is, what's the domain? The answer is the set of all reals. The range of f is a set of positive real numbers. So b to the x must be positive. So, the interesting thing about this is, okay, what if you have a negative value of x? First of all, is it possible to have a negative value of x? And second of all, what kinds of outputs are possible? Could you have negative 2? Okay, yes you can, because you can put anything in there for x, okay? The domain is the set of all real numbers. So anything is allowed to be an input. Anything can go into there for x. Well, if you put a negative 2 in there as the input, what kind of output could you have? That's going to mean a negative output, right? Wrong. For f of x equals b to the x, this is going to be b to the negative 2, which is a positive number. It's a positive number, okay? You might remember the rule of exponents. I hope you do, because you're really going to need to know it, that any number raised to the negative n power is 1 over that number raised to the positive n power. Riddle, oh my, it's gonna get crazy here. Here's a problem related to exponential functions. Suppose you received a penny on the first day of December, 2 pennies on the second day of December, 4 pennies on the third day, 8 pennies on the fourth day, and so on. How many pennies would you receive on December 31st if this pattern continues? Now, I don't think you've been able to figure that out already, and so let's stop you and ask this question. Would you rather take this amount of money or just take $10 million? Okay, well, let's figure out, what we've got here. Day 1, that's day of December. One, two, three, four, five, six, 7. And the number of pennies that you get. Of course, it doubles every time according to the pattern described by the problem. Well, 1 is 2 to the 0, and 2 are 2 to the 1, 4 are 2 squared, 8 are 2 cubed, 16 are 2 to the 4th, 32, 2 to the 5th, 64, 2 to the 6th. Of course, there are a lot more days in December, right? There are 31 days in December. And, well, that's going to be 2 to the, well, what's the pattern here? Okay. The exponent is always one fewer than the day of the month. Okay, so exponent is 1 when the day is 2. When the day is 3, exponent is 1 fewer than that, 2. When the exponent is 31, I'm sorry, when the day is the 31st of December, New Year's Eve, the number of pennies is 2 to the 1 fewer than 31, 2 to the 30. Now, if this pattern were to continue, how many pennies would you have on December 31st? You would have 2 to the 30 pennies. Is that a lot? What is 2 to the 30? That is 1,073,741,824 pennies. It's crazy. And that's why we love exponential functions, because they just give you wacky, crazy, funny, fun numbers. Now, in dollars, this would be, take that decimal point, go 1, 2 to the left, and you have $10,737,418.24. So that's more than what you would get, is more than the 10 million. And so you would be throwing away hundreds of thousands of dollars by just taking the 10 million. This example shows how an exponential function grows extremely rapidly. In this case, the exponential function f of x equals 2 to the x is used to model this problem. Use a table to graph the exponential function above. That's a common problem. Graph 2 to the x. Now, what did we say about the values of x that are possible? Well, it could be anything. The set of all reals is the domain. Well, that includes irrational numbers such as square root of 2. That could be an input. Square root of 2. It's not just integer inputs, any real number, even square root of 2. What's that? Well, that's approximately 1.414, approximately. We will use integer values in the table, though. So here's our table, and we raise all of those inputs. We make all of them the exponents with base 2, and we get these outputs. Now again, a to the negative n equals 1 over a to the positive n. So 2 to the negative 4 equals 1 over 2 to the positive 4, which is 1 over 16. So when x is negative 4, y is 1/16, just a very small positive number. And you can kind of tell how, as we go right to left, as we go from -1, -2, -3, -4, we've got a half, and then we've got a half of a half. Imagine your pizza getting cut in half as, double the number of people keep walking into the room wanting some pizza. A half of a half, a half of a half of a half, a half of a half of a half of a half. And that's that -4 1/16 that we were talking about. Well, you can keep cutting in half all day, and you're still going to have positive numbers. You're still going to have numbers that are, slightly positive, not much above the x-axis as y values, but they will be above the x-axis. That's why this graph never touches the x-axis, and why the range is the set of all positive real numbers. Range is the open interval 0 to infinity It can't be 0, but it can be anything greater than 0. Of course, for positive values of x, this graph is just going to blow up and explode, which is what we expect for exponential functions. We expect exponential or explosive growth. So here's 2 to the 0, which is 1. When x is 1, y is 2. When x is 2, y is 4. When x is 3, y is 8. 5, 6, 7, 8. When x is 4, y is 16. So properties of the graph. They all pass through 0, 1, right? When x is 0, when the input's 0, the output's always going to be 1 because of that rule of exponents, which hopefully you remember, that anything raised to the 0 power equals 1. So that makes y 1, right? Because y is this f of x. And so all the graphs pass through the point 0, 1. Just like the one we just saw, right? Okay, so typical graph, exponential function, looks like that, passes through 0, 1. All graphs are continuous curves with no holes or jumps, no gaps. The x-axis is a horizontal asymptote, right? The curve approaches it, gets closer and closer to it, but never touches it. That's the x-axis. If b is greater than 1, like the one we just did, right? That's what we did. We did b, the base greater than 1, y equals 2 to the x. That's kind of, what we have in mind with that graph over on the right. B of x increases as x increases. So the graph is going uphill as we read from left to right. If b is less than 1, b is greater than 0. In other words, 0 is less than b, as we were saying. But b could be less than 1. It could be like a half. Then it's actually going to decrease. The function is going to decrease as x increases. So we're going to see this. We're going to see how some of them have this kind of behavior. The good news is there are only two kinds of exponential functions, two families of graphs of exponential function. The increasing one and this decreasing one. Using a table of values, you will obtain the following graph. Okay, so now what do we have here? We said, what if you have b less than 1? Okay, well, that's actually what we have when we have 2 to the minus x. Because 2 to the minus x, 2 to the minus x, well, that's 2 to the, and the exponent we could think of as the product of -1 and x. Okay, because of the rule that says if you have a power raised to a power, you multiply the powers. Well, we're thinking of it this direction, with m equal to -1 and n equal to x. And so this is actually 2 to the -1 times x. Now, why does that matter? Well, we're going to do more with this. Now what we're going to do is use another rule of exponents, which hopefully you haven't forgotten, and do the well, actually we're going to use this rule that we just wrote over here, the same rule. We actually didn't even use the rule right here. All we did was rewrite -x as -1 times x, which of course it is. But now we're going to go right to left on this and power of a power this. That's what we call this rule over here, the power of a power rule. And x is the exponent with base 2 to the -1. Well, what's 2 to the -1? 2 to the -1 is 1 over 2 to the +1. Okay, well, you don't have to write the +1 exponent. This is just the xth power of 1/2. And so base b is 1/2. 1/2 is less than 1. And so we know how this graph is going to look. We just said that this is supposed to be the graph, the decreasing one. And the table of values will tell us why. Okay, so there it is. Okay, there's the graph. If you are graphing 1/2 to the x, which is a better way to think about this, 1/2 to the x on x, because that is what 1 over 2 to the x is. It's 1/2 to the x power. But if you think of it as a power of 1/2, then you can imagine your pizza example. Of course, they all go through 0, 1, but for x equal to 1, now you've got the first power of 1/2, and for x equal to 2, now you've got the square of 1/2, which is half of a half. Half of a half, which is 1/4. And then when x is 3, you've got half of a half of a half, which is 1/8. So that's why you have points like 3 1/8, 2 1/4, 1 1/2, And as always, 0, 1. But then for x negative, you're starting to get big numbers, because when you have x equal to -1, -2, now you've got negative powers of x, 1/2 to the -1. Well, the -1 exponent, you might remember, the meaning of the -1 exponent is that you're just taking a reciprocal. This is 2 over 1, or just 2. So the point -1, 2 is on the graph, and then for x equal to -2, you've got the -2 power of 1/2, which is actually going to be, now let's graph 3 to the x. Why don't you pause the video of 2. Okay, let's pause. So the explosion happens now on the left. As we go to the left, we're getting exponentially large. See if you can come up with this graph. Explosive growth as we move, or at least imagine how it's supposed to look. Proceeding as before, we construct a table of values and plot a few points. Be careful not to assume that the graph crosses the negative x-axis, even though the calculator, the graphing calculator, makes it look like it does cross the negative x-axis, or it actually makes, usually the graphing calculator makes it look like the graph coincides with the x-axis. It just kind of lands on the x-axis, and it's like right there on the x-axis the whole time as we go to the left infinitely. Remember, it gets close to the x-axis but never intersects it. So there's a table of values, and we have values like these for the negative x values, because 3 to the -1 is 1 over 3 to the +1, right? The reciprocal of 3. And 3 to the -2 is 1 over 3 to the +2, or 1/9. And 1/9 is in a decimal point. So here's a preliminary graph of 3 to the x. These are the points that we had from our table. This is copyright Elizabeth Staple, and she reserves all rights. Here's the table that we had, and we could plot more points. We could keep going here. The point 327 is on the graph, so somewhere way up here we've got a point 327. Okay, that's preliminary. Of course, what we're going to do is connect the dots. And this point here looks like it's right on the x-axis, but it is not right on the x-axis. It's a little bit above the x-axis because the y value is not 0, it's 0.1111. And a completed graph looks like this. And so that's an excellent graph, with the table, with labels. You don't just look at your graphing calculator and draw a little sketch and that's it, but you got to, in some way, you have to indicate what points are actually on the graph, and the table does that. Of course, you need exact coordinates, so don't put 0.1111 if it's really 1/9. So you should be plotting the point -2 1/9. Don't put 0.11111, put 1/9. Here's a member of the other family of graphs of exponential functions, a decreasing one. This is 4 to the -x, which is the xth power of 1/4. it's a reflection of the graph of f of x equals 4 to the x about the y-axis. Remember how when you replace x with negative x, you reflect the graph through the y-axis. And so 4 to the x, would have a graph like this. It would go through 0, 1, and it would go through the point 1, 4, and it would go through the point 2, 16. Okay? And asymptote out to the x-axis over on the left. So you get these two graphs, which are reflections of each other through the line through the line x equals 0, which is the y-axis, because we're replacing x with negative x, and so we get that reflection when we do that. And the blue graph is always decreasing. It's going downhill as we read from left to right. And as always, it passes through 0, 1, because when x is 0, y is 1, f 4 to the negative 0 is 4 to the 0, which is 1. So the point 0, 1 has to be on the graph. Properties of exponential functions. For a and b positive, a not equal to 1 and b not equal to 1. And we're just dealing with real numbers here. We have all of these old laws of exponents. Okay, we've talked about this one, the power of a power rule. When you have a power of a power, you multiply the powers. And here we see, other familiar rules of exponents. A to the x, a to the y equals a to the x plus y. So all the old rules of exponents, we want to be fresh with those. When we're solving an exponential equation, solving one, a lot of times we're going to be able to use this rule, which is if you have two exponential expressions with the same base and they're equal to each other, then the exponents must be equal. X must be equal to y. If not, a to the x wouldn't equal a to the y. For x not equal to 0, a to the x equals b to the x if and only if a equals b. So if the exponents are the same, then the bases have to be the same. And so do make an effort to re-memorize probably, these rules of exponents. And that will get it done for this objective.